Okay, so what we are now going to look at, so we saw so far P and NP problems, right? So let us look at a few more categories, or two more categories actually of problems called NP hard problems first. Okay, so we say a problem is NP hard if every problem in the class NP is polynomial time reducible to it. So it means I said there are a lot of problems in the class NP, right? So we say a problem is NP hard if I can pick every problem in the class NP and show that it is polynomial time reducible to that particular problem. Then that particular problem can be called NP hard. So let us say you have problem T. You want to show that this problem T, let us say it is the traveling salesman problem. So you want to show that traveling salesman problem is NP hard. That means we'll pick every problem in the class NP and show that it is polynomial time reducible to the traveling salesman problem. So we just showed one such reduction. The Hamiltonian circuit problem is in the class NP. So we picked one problem in the class NP and showed that it is polynomial time reducible to it. So like that, by definition, if every problem in the class NP, like the Hamiltonian problem, it has several problems in the class NP. If every such problem in the class NP is polynomial time reducible to the traveling salesman problem, then the traveling salesman problem can be said to be NP hard. That's the way we define NP hard. Now, that's the definition. If every problem in the class NP is polynomial time reducible to it. Now, do you have to really do that? So let us say if you do research, if you go to graduate school and you do more theoretical research, you'll encounter all these issues. So you have a research problem and you want to show it as NP hard. That means, would you really take every problem that are already classified in the class NP and would you go through a reduction process like we just went through one reduction here? We'll go through several such reduction processes for each of those problems to that particular research problem, like the traveling salesman problem. No, you don't need to do that. You could do that, but that will be like a more roundabout way of proving that your problem is NP hard. A more shortcut and a more smart way of doing the proving your problem is NP hard is this. You already take a problem that has been already proved to be NP hard and you show that that particular NP hard problem is polynomial time reducible to your research problem. Then you can claim, if you prove that some problem that is already proved to be NP hard is polynomial time reducible to your problem, then you can claim your problem is also NP hard, because that's what we just now did. Hamiltonian circuit problem is in the class NP as well as it is proved to be NP hard. It's in the literature. So we take up one NP hard problem, means it's already proved to be NP hard, and we show that it is polynomial time reducible to the traveling salesman problem. That means then the traveling salesman problem is also NP hard. Now why is that? Just apply the definition of NP hard. If that Hamiltonian circuit problem is already proved to be NP hard, that means all problems in the class NP except this say T, because T is a new research problem we're looking at. So every problem in the class NP basically is polynomial time reducible to the Hamiltonian circuit problem, because that's the definition of NP hard. So if I say the problem H is NP hard, it means all problems in the class NP are polynomial time reducible to it. So this T is a new problem that we're working on and it is also in class NP. So that's why I say all problems other than the problem T. So it's like kind of what you call commutative. So all problems in the class NP are polynomial time reducible to this Hamiltonian circuit problem. And so it's transferable. So this problem H is now polynomial time reducible to the problem T. So that means all problems the class NP are actually polynomial time reducible to the particular research problem, right? Because if say A is polynomial time reducible to B and B is polynomial time reducible to C, then A is actually polynomial time reducible to C, because the sum of say the two polynomial time complexities is also going to be a polynomial. We have seen that several cases. So if one reduction is V cube, the other is V square, the total time complex is V cube plus V square, which is V cube, and it's also a polynomial. So that means if we are able to show one NP hard problem is polynomial time reducible to the research problem we're looking at, that means every problem in the class NP are also polynomial time reducible to the research problem. So that is how you show a problem is NP hard or not. Okay, we'll just take up one NP hard problem, one problem that is already proved to be NP hard, and show that it is polynomial time reducible to the new problem we're looking at. So that's something you have to be clear about. Okay, so if you have any questions, you can ask. Now let me, if you actually I'll complete this, and if you have any questions, you can ask that time later, because that will make it actually a complete package. All right, so let us do this NP complete problem. So this will actually put everything together. So when you say a problem is NP complete, a problem is NP complete if it is both in the class NP as well as in the class NP hard. So that means it's time to look at this figure now. So we saw what is class NP, which means you have problems for which you have algorithms that can give you only a non-deterministic solution in polynomial time. So you don't have algorithms for which for problems that will give you a deterministic solution in polynomial time. So that's what class NP means. Class NP hard means every problem in the class NP is polynomial time reducible to a particular problem. So remember that the definition of NP hard does not require a problem to also be in the class NP. It could be a problem that is not even in the class NP. One such problem is a halting problem, which is by definition given a program and its input, will it run forever? It looks like a simple problem. Given a program and input for the program, will the program run forever? That's what we have to know. It's a decision problem. It's called the halting problem. Now, this problem is not in the class NP, but every problem in the class NP can be reduced in polynomial time to this problem, to the halting problem. So it is an NP hard problem, but that is not in the class NP. Now, if a problem is in the both in the class NP and is as well as NP hard, then it is said to be an NP complete problem. So the NP complete problem is basically the intersection of these two classes of problems. A problem is said to be NP complete if it is both in the class NP as well as in the class NP hard. Then all those problems that are both in the class NP and NP hard are said to be NP complete problems. Now, why it is a very special category of problems, NP complete? You might have heard this terminology in the other courses or in the website on literature. So, why it is a very special category of problems? You think you have heard like that. The reason is very important to understand. Again, what I mean by NP hard, every problem in the class NP is polynomial time reducible to that particular problem. Then we say a problem is NP hard. So, an NP complete problem is also NP hard. That's something you have to figure out by definition, right? So, a problem is NP complete if it is both in NP as well as NP hard. That means an NP complete problem is also an NP hard problem. So that means every problem in the class NP is polynomial time reducible to the NP complete problem. So now if you have a deterministic algorithm, or if you have let us put it the other way, if you have a polynomial time algorithm that can give you a deterministic solution for an NP complete problem. So what does it mean? So you have a problem, let us say it's a graph problem, for which given any graph, it is guaranteed to give you, say, the optimal solution in polynomial time. It is deterministic. So given any graph, that algorithm is going to give you a deterministic solution in polynomial time. Then it means you have a polynomial time algorithm to solve a NP complete problem. That also means you have polynomial time algorithm to solve an NP hard problem. And which means what? Every problem in the class NP can be polynomial time reducible or reduced to that particular problem, for which you have a polynomial time algorithm that can give you deterministic solution. And that means every problem in the class NP can be solved in polynomial time. So that will mean P is equal to NP. Is that clear? So all these things will kind of merge. All the classes will be one single class. So if you have a polynomial time algorithm for one NP complete problem, right? So that means what? All problems in the class NP can be polynomial time reduced to that particular problem, because NP complete problem also means it's NP hard. So if every problem in the class NP can be reduced in polynomial time to that single problem, and you have a polynomial time algorithm for that problem to give you a deterministic solution, then every problem in class NP can be solved deterministically in polynomial time. So if every problem in the class NP will now have an algorithm that can give you a deterministic solution in polynomial time. So then P will be equal to NP, right? So, but the way things are now is nobody has come up with a polynomial time algorithm that can give you a deterministic solution for any NP complete problem. So right now it is like this. But if somebody comes up with a polynomial time algorithm that can give a deterministic solution for NP complete problem, then P will become equal to NP. Nobody has come up with, but the thing is, can anyone come up with some algorithm in the future? It's not possible to say yes or no. Someone may come up with, it may not be possible to come up with. So the question of P equals NP. So if you're interested in this area, you can just type this in Google. P equals like question mark, NP or not, and you'll come across a lot of sites talking about that. So this is an open problem. Will P be ever equal to NP or not? As of now, it is not equal to NP. That because there is no polynomial time algorithm that to give a deterministic solution for even one NP complete problem. If somebody comes up with some algorithm for at least for just one NP complete problem that can give a deterministic solution in polynomial time, then P will be equal to NP. But so far not. But can you prove it is not possible for P to be equal to NP? And the answer for that is also no. We cannot prove P will never be equal to NP. That's also not possible. So that's why I say P not equal to NP or not is a dilemma. It's not. There's no way you can tell that until now, and possibly in the future also. So it's considered to be always open-ended problem, and the way the problems are kind of to be considered is like this. Okay. So let us see some examples, sample problems that fall in each category, and then we'll start moving to some practical things. So with this we'll finish the theory. So for the class P, of course, you saw a lot of problems. Optimization problem, like minimum spanning tree, even sorting problem is an optimization problem. You are trying to sort in the minimum starting in the increasing order. So we can say it's an optimization problem. Shortest path problem, decision problem, two colorability. So all these are in the class P, because that means for all these problems, let us say sorting problem, that's more easy to also understand. If you come up with merge sort of complexity n log n, doesn't matter what array you are given, it always sorts the array. That's the deterministic part of it, right? So this may be clear. So if for any array, that sorting algorithm, merge sort or insertion sort, or sorting algorithm you come up with is guaranteed to sort the array deterministically. So it's not that for some arrays it will sort and some arrays it will not sort. No, it's not like that. So that's why we say the sorting problem is a deterministic problem, because for that problem you have algorithms that can give you a deterministic solution in polynomial time. Similarly, the other problems listed here. Whereas the decision version of the minimum spanning tree problem is in the class NP. Okay, so that means you don't have polynomial time algorithm that can give you the decision solution for the problem in polynomial time. Okay, in deterministic fashion. In a deterministic fashion. So, given arbitrary graph with edge weights, the problem of is there a minimum spanning tree of weight less than 30. Now I said earlier you run once on the given graph, but it depends on the value, right? So for example, let us say the let us say the minimum edge, the threshold. Is there a minimum spanning tree of weight less than a threshold? Now, what is that threshold? How is it related to the minimum weight of a spanning tree? There are a lot of combinations. So that means it's like an exponential time problem. You cannot say that in polynomial time. We have to try out all possible combinations before we say an yes or no answer. So that's why it's a NP problem. Now for the class NP hard, we have the halting problem, and the optimization version of the traveling salesman problem is also the class NP hard. Now NP complete, you have the decision version of the traveling salesman problem. So is there a minimum weight 2 of weight, say some value? That's the decision version. Now the Hamiltonian circuit problem, the maximum click problem. So we have not seen what a click is so far. We'll see that soon. So all these things are examples of NP complete problems. Okay, so for your quiz for your upcoming assignment, you are supposed to know some examples for each class. And also you are supposed to know the definitions of NP, NP hard, NP complete, and the polynomial reduction and all this, the theory part. Okay, so of course the quiz is going to be posted in Canvas and you can take it in Canvas, so you can refer to all these materials, but you should know the definitions and all this stuff and relation between these categories of problems. Okay, so with that, let me save this video. If you have any questions, you can ask over the microphone or type any message.